Saxon Algebra 2, Lesson 17. Our topic today, well, we've got a two-parter. We've got an algebra topic, and then we have a short geometry topic. And if you have to have two topics in one lesson, which John does a lot of in this book, I like it when the first one is algebra and the second one is geometry. It just mixes things up in your brain a little bit and feels better. The first topic is subscripted variables. Remember that subscripted variables are just little letters attached to our big letters, and the whole purpose of a subscripted variable is just to help us connect the words of a word problem to the equations that we create. It's designed to just help you make the words fit into the equations better. So let's look at an example. Right now, we're not doing any of the actual word problems. We're just remembering how to manage the subscripted variables when they're already written into an equation. So John gives us a system that looks like this. I'm sure you recognize it. We did a lot of problems like this last year. And we remember that, oh yeah, this whole, this is number of nickels and number of dimes, right? And then we have one equation with that and then a second one, and we're solving for how many nickels and how many dimes we have, right? These are the coin problems that I believe we did last year. I'll tell you, sometimes the difference between Algebra 1, Algebra 2, and Advanced Algebra gets kind of muddied in my brain because, you know, I'm going back and forth between them all the time. So, in any case, these are coin problems that involve nickels and dimes, and that's why we put the letters the way we do, the number of nickels, the number of dimes. Again, it just helps us connect the words to the equations. When we're working with them, we just treat them like a single thing, right? We could have used X and Y, but then we would have had to say, oh, X equals the number of nickels. And that just makes it, that just adds a layer of confusion. We'd rather let our variables sound just like the words. So there's nothing special about how we work them. We just learn to ignore them. In this one, John did not tell us whether to use substitution or elimination. So we get to choose. All right, and since you're not here, I get to choose. Just to help us talk about them, I'm going to put letters in front of them. And I think what I would like to do is I would like to multiply this first one by -5, and then it will drop off, the number of nickels will cancel out. So I'm going for canceling this. So I'm going to multiply -5 times equation A, and I'm going to write the answer down here. That would be -5 times the number of nickels, and -5 times the number of dimes equals -200, right? Multiplied each one of these by -5 to get that. Wrote a little note to myself so I would remember. Now what I'm going to do is add B plus -5 times A. I'll put parentheses around him too so he feels special. All right, so I'm combining these two. That cancels. 5 times the number of dimes equals 50. Oh, I like it. So we get the number of dimes equals 10, right? And then the number of nickels, we'll look back at our original equations and find one that looks like it'd be helpful. And I like this first one. They have to add up to 40. So my brain tells me that this must be 30, and then I just do a quick check to make sure I haven't gone crazy in my old age. Not that I'm old. I don't worry about stuff like that. And that's our answer. That's correct. All right? So the subscripted variables don't hurt once your eyes just get used to seeing them and recognizing them for what they are. We're also going to get back to our old friends, the distance problems, right? With the rate times the time and the Lord of the Rings and the Princess Bride and all of that. But we're not going to get involved in the stories yet. We're just going to look at how the equations look. And so here's our second problem. This is our only other problem on this topic. We have got a base equation that looks like this. So what this is telling us is that there are rates and times of somebody who's named M, let's say Marianne, and rates and times of somebody else. Let's say Walter. Let's say this is about Marianne and Walter. So that's our base equation, and then we have a little bit of additional information. The rate of Marianne equals 40. The rate of Walter equals 60. And then the times equal 5. All right, so we're given all this information and we're asked to solve this system. Again, we don't know the story, and we can see rate of Marianne, rate of Walter, and the times of the two of them. We don't care though. Those subscripts don't bother us in the least. We just treat them like they're normal letters. So what I want to do is I want to take my original equation and use buckets for these numbers. RM equals 40, RW equals 60. But now what do we do about this? We don't have any place to write TM plus TW. So I'm going to rearrange this so I can substitute it in. I'm just going to subtract the second one. You could subtract either t variable to the other side. I'll choose to do it that way. So TM equals 5 minus TW, and then this one I'll just leave as TW, and they match, so I know I'll be fine. Yay. Now I'm ready to, let's see, I'll have to distribute here, and then this is just fine. So this will be 200 minus 40 TW plus 60 TW equals 260. Well, let's see, I combine these as like terms, and in the same step, I'll subtract the 200. Swim it over here. This cancels. Those two add together to give me 20 TW equals 60. John, you always make it work out so fun. And we get that the time of Walter equals 3. We don't know 3 what? Hours, minutes, seconds, light years. I don't know. It doesn't matter because we're not worrying about words in this problem. How do I find TM? We're supposed to, quote unquote, solve the system. That means find all the variables, by the way. John's telling us to find them all. We know that they add up to 5, so again, this has to be 2. I double check it just to show that I'm paying attention, and that's my final answer. Yay! Fun, right? So this is our review of subscripted variables. They don't bite, they serve a purpose, they help us connect words with the equations. Once your eye gets used to them, you won't feel even the least bit concerned about seeing them there. Okay, let's do a little geometry. Just a very little. This is called angle relationships. That sounds steamy, doesn't it? (17.3). We get to draw a picture. Are you ready? 2 parallel lines. We know they're parallel because they have these little things on them, right? That's the symbol that means these dudes are parallel. They're karate chopped by a transversal. Pretend it's perfect, it's not. And then we have information written in the corners, which we remember, oh yeah, that's the thing about these transversals, these karate chop lines, is that they create this special pattern, right? Between the angles, they create the large, small, small, large thing. So we're supposed to find x and y. Well, the tricky thing is, how do we start this, right? How do we find some solid ground? I can see this is the little angle, and this is the little angle, right? Because it goes large, small, small, large, large, small, small, large, right? That's always the pattern that transversals make. Large, small, small, large, large, small, small, large. If by any chance a transversal was ever to go like this, the pattern works the same. It's just that you start with the small and go to the large, right? And all you have to do to know which angle you have first is just like literally look at it, right? You can see this is larger than 90 degrees. So we know we're following this pattern, so we just look at this and go, okay, if I put these two, if I try to do something with these two, they each have two variables. That's not gonna work. Somehow I have to start by using this number. And there's two ways to do that. I can see that this angle, whatever this weird thing means, plus this is equal to 180, right? Because that's true on all of these. Is that equals 180, that equals 180, right? There's different ways we can find those straight angles going through here. So I could say that 7x minus, not plus, 2y plus 50 equals 180. That would be a good starting point. I could do that. Or I could my eye could catch the fact that these two are the same. So I could say 5x minus 10y equals 50. All right. And what I see is that I'm going to need to use both of these, aren't I? Because I've got an x and a y in both of my equations. And I can't solve any further as is. So that tells me, oh, you're actually a system of equations. So what I'm gonna do is just clean up this top angle and write it together as a system, because I can subtract the 50 from both sides here. And that will give me 7x minus 2y equals 130. And it doesn't have to be, but this is the way we like our systems of equations to look. An x, a y, and a plain number on the other side of the equal sign. An x and a y and a plain number on the other side of the equal sign. All right, so now our equation, our system is even better. This is our A, this is our B. How are we going to solve this? I'm looking down the columns. I don't want to multiply by 7 and 5. That seems like a lot. I'd rather adjust this one, because what we can do is we can multiply A times minus 5, and that will get the y's to cancel, right? I can just multiply one of them. So I'm going to do that. I'm going to multiply A times minus 5. So that'll give me minus 35x plus 10y equals minus, and that will be 650, 500 plus 150. Right? Now, I'm going to add these two together, right? So that'll be B plus A times minus 5, these two. So that gives me minus 30x, the y's cancel, equals minus 600. Ooh. I divide by 30, minus 30, and I get x equals positive 20. I like it. That is the first part of my answer, but now I need to solve for y as well, don't I? And notice this is the kind of problem where we started with geometry, but we used that to build a couple equations, and now we're using algebra to solve it. In an example like this, where I've run out of space but I don't want to turn the page, what I do sometimes is I make like a little box to finish my work in. And what we want to do here is we want to solve for y. We want to take either one of our original equations and we want to plug this in for y or for x rather, and solve for y. I'm going to choose B. So 5 times 20 minus 10y equals 50. Does that sound right to you? 100 minus 10y equals 50. Subtract 100 minus 10y equals minus 50. Y equals 5. And so for my final answer, I'm going to make one more box. And I'm going to write x equals 20, y equals 5. And if we wanted to, we could write it as an ordered pair. But in this problem, I think because of the geometry context, I don't want to do that. I think it's fine just to leave it like this. That's the right answer. Yay. This was a tricky problem because we had to recognize that even though we could set up two different equations, neither one of them on their own was going to get the job done. We had to put them together in a system in order to solve for x and y. Oh. I promise you I'm not tired and I'm not the least bit bored. I could do this all day long. Okay, that is the end of lesson 17. Thank you for your kind attention. Goodbye.